my pleasure to introduce Freddie Manners of Stanford University, who will be speaking on good bounds in some systems of true complexity 1.
Great. Well, thank you very much for the opportunity to speak here. I think many people in the audience will know what this title means, but I sort of will nonetheless spend some time explaining what it is I'm actually talking about and setting the scene. And that'll take a little while, and then I'll get on to some new results later. So I'm going to fix G some finite abelian group. For our purposes, G is going to be either Z mod nz for n prime, or fp to the n. P is also prime, and n is sum. There's a number, and okay, I mean this one is the case of this one when n is equal to 1, so you can just think of this case. And the kinds of questions we're interested in are if I have some subset of G, then I want to count solutions to some system of linear equations. That all lie in X. So for instance, I might be interested in counting Schur triples, so that would be the count over X and Y in X, X and Y in G of indicator of X of X, indicator X of Y, indicator X of X plus Y. So I'm counting all the pairs X, Y, X plus Y, which all simultaneously lie in X. Or maybe I'm interested in counting 4-term progressions. That would be the expectation over X and Y in G of indicator X of X, X plus Y, 2y, X plus 3y. Switch to this board. And okay, in general, case 3, I'm going to fix some, so look at some system of linear forms. So these will be phi 1 up to phi r or something. So these are linear forms from ZD to Z. I'm going to change this pen. It's big now. And then I'm interested in counting the expectation of x1 up to xd of all the things where phi 1 of x1 up to xd and phi 2 of x1 up to xd all the way out to phi r of x1 up to xd all lie in my set X. So okay, and so this is case 3. I'll write capital phi for my system of linear forms. And okay, 1 is the special case where whatever I've got, d equals 2, r equals 3, phi 1 of xy is x, phi 2 of xy is y, phi 3 of xy is x plus y, whatever. And the other one is a special case where d is 2 and r is 4 and so forth. But this is kind of the most general question you might want to consider. I'm abusing notation slightly horribly by interpreting this phi as also a map from G to the D to G, either by abusive notation or taking a tensor product, however you want to think about it. Okay, and the key observation in this whole subject, if I've got a pen which is better than that one as well. Let's try this one. So, observation. Originally, due to Gowers, let's say, or it's a long, complicated story which I won't go into, but let's say specifically in the case of number 2 for 4 APs, that these counts are controlled by Gauss uniformity norms. So what I mean by that, there's a few different things it could mean, but roughly the simplest statement you might want is that if I have a set X which is very quasi-random in the sense that it's close to the identity, the identity function with some density alpha in some Gauss norm. So if X minus alpha in some Gauss norm is very small, then this quantity, just write this thing is roughly equal to what you expect for a random set of density alpha. So alpha to the d plus big O of, so it's less than equal to epsilon, and this is something like, I'll just say little o, little o1 as epsilon tends to 0. So this was, I guess, in the case of Scher triples or something, then the correct uniformity norm to take is U2, which basically just translates as Fourier analysis. This is very classical. And then in the case of the four-term progressions, you have to use the U3 norm, which is sort of quadratic Fourier analysis. And so Gauss showed that you can get a statement like this basically just by using lots of applications of Cauchy-Schwarz, and also that this number 3 is best possible. So also you can't use U2 for system 2. Yeah, sorry, question.
This is a bit of a side question. I was just wondering, in these things that you're saying you're going to say, can I replace 1x by something more general, like a density?
Sure, yeah, absolutely. Yeah, the result I'm going to state is sort of, I'll say something sensible for any complex valued function as long as it's bounded. Yeah, so something that's morally bounded, sort of L infinity norm of 1 or something, then yeah, everything would be true. Yeah, okay, so the kinds of questions, maybe I should say first that, so in this general case, the question of, can I get this kind of control over these types of configuration counts using one of these Gauss norms? This was worked out by Green and Tao in their equation in their work on linear equations and primes, 2010 or something. I mean, it's not a deep statement. It's basically just saying, take the Cauchy-Schwarz argument you do and figure out what it tells you. So maybe I should say what they get. So they say something like the following. Sorry, first I'll introduce a little bit more notation just to avoid writing it again and again. I'm going to write lambda phi of f1 up to fd, fr, sorry, to be this multilinear average f1 of phi 1 of x1 up to xd. That's any better. Okay. So this is for any functions f1 up to xr from G to complex numbers. So what Green and Tao proved is that I'm going to define some number. So say that the system phi has Cauchy-Schwarz complexity less than or equal to s. If the following technical condition holds, and this says that, well, okay, I'll modify this slightly. Let's say that the phi has Cauchy-Schwarz complexity at most s at some index j, and I'll put in brackets mod p. If the following holds, so whenever I can partition all the indices apart from j into S plus 1 classes. I1 up to IS plus 1, such that the linear form phi j is not in the span of the other linear forms. Phi I for I in ik for any k. Then if that holds, I get some bound of the following type, that lambda 5 f1 up to fr is at most fj us plus 1, provided all these functions are bounded. Okay, so this is their definition of Cauchy-Schwarz complexity. I mean, basically, in their work, they only really cared about this number being finite. So, given a system of linear forms, is there some number, and then I have to work with some uniformity norm us plus 1, but I don't really mind too much what it is, as long as it's not infinity. And right, the proof of all these things is just by lots of applications of Cauchy-Schwarz. And again, I don't want to spend the whole of the talk writing up lots and lots of applications of the Cauchy-Schwarz inequality in gory detail on the board, but I probably owe it to non-experts to do at least one of these just to see how it goes. So let's say for my Schur triples, I've got this lambda f1, f2, f3, lambda phi is equal to this expectation. So I'm going to write this, in a funny way. So first take an expectation over x, and then take an expectation over y. Sorry?
A Schur triple is a configuration of the form x, y, x.
Oh, thank you, yes. So phi 1 equals x. Phi 3 equals x plus y. So this is what I called example 1 earlier. Okay, so I can write this this sort of counting function of lambda in terms of this expectation, where I've sort of taken out the x dependency and put that separately, and then I apply Cauchy-Schwarz, thinking of this as the x variable as some average, and then this is one function and this is another function. So I get this guy and some other thing. X, expectation over y, squared. Here's something like this. And then if I take this thing and expand it out, that's equal to the expectation over x, y, and y prime, f2y, f2y prime, 3x plus y, prime. And then I apply Cauchy-Schwarz again, and the way I'm going to do that is to, again, slightly mess around my order of summation. So I'm going to take y and y prime out the front and put the integral over x in here, and then this becomes bounded by y prime. That will get squared half, and then I get some other thing, expectation over y prime x and x prime of this rubbish. Prime 3 of x prime plus y, 3 of x prime plus y prime. And this is just precisely f3 u2. Squared in this case, because missed out a factor of a power of a half, but yeah, that's what you get. And so the way that this is a special case of the proof of the general Cauchy-Schwarz complexity result is that I'm interested in f3, so I'm setting j equals 3, and I'm going to pigeonhole these three forms x, y, and x plus y, where sort of this is my first class, and so this is the entirety of I2, and this is the entirety of I1. And you observe that x plus y is not in the span of x, and it's not in the span of y, and therefore this goes through and it gets you that bound. OK, so slowly converging on the things I want to say. Oh yeah, comment again that I missed. This type of control here, I'll call this sort of Roman 2 or something, whereas before I had this kind of control, which I'll call Roman 1. So the bound Roman 2 implies the control. So if I have this strong thing that, for any functions f1 up to fr, complex valued L infinity bounded functions, if I can get this bound of type Roman 2, then that sort of implies by a standard argument that if you're suitably pseudo-random in the s plus 1 sense, then you'll have close to the correct number of counts. So this is kind of really what we want. So, right, an observation by Gauss and Wolf is that in the case of four-term progressions, we had an upper bound and a lower bound, right? So we said that we can control the count of four-term progressions by the U2 norm, the U3 norm, sorry, and we can't control it by the U2 norm. So maybe I'll briefly say why that was. So for APs, I can take f1 of x is equal to e of alpha x squared, f2 of x is e of minus 3 alpha x squared, f3 of x is e of 3 alpha x squared, and f4 of x is equal to e of minus alpha x squared. And then the lambda thingy for 4 APs of these functions is just 1. So the reason for that is that x squared minus 3x plus y squared plus 3x plus 2y squared minus x plus 3y squared is equal to 0 for any choice of x and y. So when you sort of plug in these exponential phases into your counting function, just every term is identically 1 and you get 1 at the end. But these functions definitely aren't controlled by the U2 norm. They're very, very small in the U2 norm. So, right, you have an upper bound and a lower bound and they match. And the observation by Gauss and Wolf is that often, in fact in general, well, maybe typically, the upper and lower bounds don't match. So there's some bound that comes out of this Cauchy-Schwarz argument, some technical linear algebra thing that says I can bound this by the US plus 1 norm for some s, and then you try and sort of construct something that shows that you can't do any better, and well, you get some different s which says I can't do better than this other s because I can find these bad examples, and these are not the same number. So
Excuse me?
Hi, yeah, sorry.
Tiny question. In your 2 there on the right-hand side, are you missing the power on the norm?
Yeah. In this case, the power is 1. Oh, yeah, sorry. So when I went from this line to this line, I lost an exponent of a half, just in my notation.
Okay.
So this is really square rooted, and you get a quarter here. Yeah, thank you. OK, so you could define the true complexity. Let's call it S true of my system phi as the smallest s such that phi 1 to the s plus 1 up to phi r to the s plus 1 are, so these are polynomials in variables are linearly independent. I mean, this is not quite how they defined it, but they made a definition which you can then prove to be equivalent to this, so which I'll come on to. So, and this basically says what's the best bad construction? What's the best lower bound you can make? Where I mean like in this way. So yeah, for which S can you construct a good lower bound? And they conjectured that when these numbers are not the same, so if S Cauchy-Schwarz, let's call it, is not equal to S true, then S true is the truth. So the philosophy here is that this Cauchy-Schwarz complexity is just some number that comes out of this argument. It's not essential in any way. It's just some rubbish. It's less than infinity. That's good. But whereas what's really going on is you should be looking at whether you can find some polynomials which you can plug into F1 up to F4 that make this number 1, and that's what really determines the correct complexity. So they conjectured this. They also proved it in some cases. So proof. So Gauss-Wolff. I think this is officially 2010, but it's all sort of rubbish because for any dates in the recent past, the date it was published and the date it was put on the archive are completely different. So here it was proved in the case of S true is equal to 1, S Cauchy-Schwarz is equal to 2, and G is Fp to the n, for P fixed, but not too small. And then a bunch of other.
Sorry, this is what's the statement exactly?
Sorry, so right. So the statement is, in any situation like this, I have a system of linear forms where the Cauchy-Schwarz complexity is 2, the true, and that's for every j, and the true complexity is 1. Then you get a sort of a 1-type bound. So in these cases, they prove that if I have a set which is close to uniform.
Is it obvious from the definition that the true complexity is at most the Cauchy-Schwarz complexity?
Right, so that's the content of this. Oh, I see. No, right. You're right. The way I've set it up, no, that's not obvious. It is true. I mean, it's some linear algebra, right? Like it's a problem that belongs purely in algebra. But yeah, so I'm slightly lying insofar as the original definition of true complexity is just the correct answer to this question, and then you show a lower bound that says that it's at least the number that I made in that definition. But yeah, and then, right. So a roundabout way of proving this is to say, if somehow there was some algebraic mishap so that what you were saying wasn't true, then I could both find a bad example and prove that a bad example doesn't exist, and therefore that would be bad. Yeah. Thank you. That's, okay, so this was one paper by Gauss and Wolff. There are going to be 4 of them. So Gauss and Wolff, paper 2 in 2011, I think, is basically the same but better. So good they proved it again. So basically the error term you get in this 1-type bound, which I never said anything about it being polynomial or whatever, got quite a lot better in this second iteration. So they showed that if x minus alpha u s plus 1, which is u2 in this case, I suppose, is at most epsilon, then this error term is something like log 1 over epsilon. Whereas here the bound was sort of ineffective. Another paper of Gauss and Wolff again in 2011 got S true equals 1, S Cauchy-Schwarz equals 2, but now for Z mod nz, where n is some large prime. And then Green and Tao in 2011, I think, showed the same thing. Sorry, the one more Gauss and Wolff paper I haven't finished yet. Also in 2011, they show for G is Fp to the n, and any S and S true and S Cauchy-Schwarz. So final couple of literature pieces. So there is then a result of Green and Tao. You sort of complete the square by showing the general case for Z mod nz, which is a different argument. And then there's a couple of papers.
Sorry, n is not prime anymore?
Sorry, here capital N is some prime, but the point is, this case was when p was some small fixed prime and n was very big, little n was very big. And this is,
Depend on p, so
yeah, here the errors might depend on p, that's correct, yeah. And
so that's why you said general, because they're incomparable, the last two lines you wrote.
this and this, yeah, so these are both doing the general case of like, you know, any Cauchy-Schwarz complexity you want, any true complexity you want, but they're working in completely different domains, and yeah, the proofs are different and incomparable for those two domains. Yeah. Okay, and then there's Levin Hatami in 2011, who sort of upgrade the Z mod, sorry, the fp to the n to a 2-type statement. Sort of. I mean, the bounds are still terrible. So sorry, here. So fj. So if I broaden the definition of a type 2 statement to mean anything that tends to 0 on the right-hand side, then they show one of those, but the dependency was still pretty bad. And then there's Hatami and Lovett, 2016, who handle small p. So all these FP results previously were for p like, you know, sufficiently large depending on the system you're dealing with, you know, like not 5 or something, and they handle all the way down to the bottom.
What was the type 1 statement?
Sorry?
So you said type 2 statement. What was type 1?
Sorry, yes, I'm distinguishing between saying if I have a set that's close to uniform, then it has the right count, to this slightly stronger thing where I'm saying for any complex valued functions here, if any of them is small in the US norm, S+1 norm, then this expression is small. So yeah, there's some sort of technical improvement to go from the first case where you only have to deal with one function at a time.
The difference is that you allow distinct functions in your product.
Yeah, right, that, yeah. Thank you. Okay, cool, so again, I'm half an hour without really saying nothing new. So sort of from a qualitative point of view, we're pretty much done with these results. They've sort of chipped away at all the cases. And we now know that it is the case that true complexity is just this algebraic thing where you have to take these powers and check if they're linearly independent. I'll say very briefly just out loud what goes into these proofs. I mean, they're all roughly along the same lines as the original Gauss-Wolff approach, which is, okay, when you have true complexity 1 and Cauchy-Schwarz complexity 2, so this is all about just deciding whether I'm controlled by Fourier analysis or not, which feels like it shouldn't be a hard question, but is. Because I've got Cauchy-Schwarz complexity 2, I know that I'm controlled by the U3 norm. So I know I can do quadratic Fourier analysis. I apply the inverse theorem for the U3 norm, which tells me that I kind of only have to worry about functions that are a bit like this. So my functions sort of are all quadratic phases without loss of generality, because anything else I can get rid of. But you're not anywhere near done at that point. I mean, it feels like maybe you can then, you know, we know when you can succeed 100% with these quadratic phases, but you need some sort of rigidity result which says either I can succeed 100% using quadratic phases, or I fail miserably using quadratic phases, and there's kind of no in-between ground. And that's definitely not a trivial argument. That's, you know, many, many pages of hard work. Okay, but qualitatively we're sort of done. There are a few remaining questions. So let's say question 1, sort of very respectful question to ask. So what are the bounds? And by bounds I mean the error terms. So in these cases, some of these cases when the true complexity is 1 and the Cauchy-Schwarz complexity is 2, you get this sort of log-log type bound that I mentioned here. So you have to assume that this is pretty darn uniform before you get anything effective about the counter equations. And that's the best over all these cases. Like everything else is ridiculous Ackermann tower type rubbish. And that fails because we use the inverse theorem for the Gauss norms when S was, use the inverse theorem for U4 and above, and those don't come with effective bounds. So that's pretty grim. And so, but what's the truth, right? So in the cases where we had Cauchy-Schwarz complexity, we just get this lovely polynomial. It's just like, you know, you can replace this quantity by just epsilon. So yeah, that would be great. Question 2. Is sort of, do we really need the inverse theorem? Or sort of, if you prefer, like, why isn't there an elementary? Sort of argument. So in these nice cases where the Cauchy-Schwarz complexity and the true complexity match, then we get lovely bounds coming out of just applying Cauchy-Schwarz some number of times. In these other cases, it seems like we're sort of forced to throw all of additive combinatorics just to conclude even that some system of linear equations is controlled by Fourier analysis. Why do we need to do that? Is there some way of saying that it's essential to be able to do this? So one thing you could try is sort of, if you can show that the bounds are not polynomial, then you can rule out some sort of approach using just a few applications of Cauchy-Schwarz, because that would have to give you a polynomial bound. If you could show that the correct true bound was super polynomial, then you could show that you have to do something a bit complicated here. Okay, so both these questions in a less mangled form were sort of in one place by Gauss and Wolf. Question 3 I sort of made up. So when S true is not equal to S Cauchy-Schwarz, the bound depends on the forms. So by that I mean, so the bound coming out of these proofs depends on what the actual coefficients are. It's not just good enough to know that your system of linear forms has Cauchy-Schwarz complexity this and true complexity that. The proofs want to inspect the actual sizes of these integer coefficients and check that they're not too large. And the bound depends on how big the integer coefficients are. The bigger the coefficients are, the worse a bound you get. Okay, if you're working mod p, then that question doesn't really make sense. Do they depend on p, right? So if I'm working in p is fixed, p is like 7 or something, there are only finitely many systems of linear forms, mod 7. So I could just take a sup over all of them, but then the question is, does the correct dependence depend on p, on the value of 7? So yeah, it's just a question I made up. I won't be able to answer these questions in anything like the general case, but I'll talk about the special case where I have 6 linear forms, so r equals 6, and d equals 3, so 6 forms and 3 variables. So standard example might be I get phi 1 x, y, z is x, and then this is going to be y. X, y, z, x plus y plus z, 2x plus 3y plus 5z, and 7x plus 11y plus 13z or whatever, some rubbish. Generically, a thing like this will have true complexity 1, but Cauchy-Schwarz complexity 2. So if I want to count these configurations, I can do it using Fourier analysis, but that's a hard fact. So this is sort of the smallest non-trivial case. So for any strictly smaller configurations, it turns out that the Cauchy-Schwarz complexity and the true complexity are the same. So let me say what I can prove after quite a long time. So theorem, let's call this theorem 1. So this says, I'm going to answer, first of all, the question I made up. So an answer to question 3. And the statement is going to be, yes, this is essential. So unlike the case of where the Cauchy-Schwarz complexity and the true complexity are the same, and just the bounds are lovely and uniform and don't depend on anything, in the cases where, in this particular case anyway, where I have a system of Cauchy-Schwarz complexity 2, true complexity 1 in 6 forms and 3 variables, the bounds have to get worse as the coefficients get bigger. So a technical statement of that is as follows. So for any p large, p is going to be plus or minus 1 mod 8, then there exist forms phi 1 up to phi 6 in, say, from fp3 to fp, and functions f1 up to f6 from, let's say, fp to the n, no, just fp to the complex numbers. They're all bounded such that lambda of f1 up to f6 phi is quite big. but the U2 norms are all quite small. Okay, but the system does have true complexity equal to 1. So the key point about this theorem is that I haven't told you anything about the coefficients of phi1 up to phi6. They're arbitrary numbers mod p. And in this setting, just the result we want isn't true. Like if I'm allowed these coefficients to be as big as I possibly want, then I can do as bad as I possibly could. I can make this counting function very, very large, but all the U2 norms very, very small. So somehow I think that there are many good reasons to suspect that you can't have a truly elementary argument for this, where you just apply Cauchy-Schwarz a few times. So one piece of intuition might be that how is it going to detect the difference between true complexity 1 and true complexity 2, right? There are some systems of 6 forms and 3 variables which have true complexity 2. How is a simple argument going to know the difference? It's just a question of whether these things are linearly dependent or not. I mean, that's a hard question. But this is a different piece of intuition that says if there were an argument proving this case that only used lots of Cauchy-Schwarz, it would have to use Cauchy-Schwarz arbitrarily many times. So you'd somehow have to inspect the forms that you're given, look at the coefficients, and based on those coefficients, come up with some Cauchy-Schwarz argument whose length is going to become large as the coefficients become big to prove a bound on true complexity in that case. So that seems kind of unreasonable.
Can you do that? I mean, it's come up in other contexts before.
Right. I mean, it's not totally unreasonable. I'm setting myself up here. So theorem 2 says in this setting, so for any p and any n, and these 6 forms, that's true equals 1, then the counting function is bounded by fj u2 to the 1 over c for some constant c that depends on phi. So this has answered question 1 about the bounds. Like the bound here is polynomial. It's as good as you could hope for. And the answer to question 2 is the proof is just Cauchy-Schwarz. So the proof of theorem 2 will be to say, you give me a system of linear forms, I'm going to inspect them, I'm going to construct a very, very long Cauchy-Schwarz argument, and this will give me this polynomial bound that I'm looking for. And yes, by theorem 1, I had to do this. I couldn't just do it 4 times and stop. So maybe a couple of remarks. Currently, C phi is, it's explicit but pretty bad. I think, so working over large characteristic, P is very large, C is exponential in the size of the largest coefficient of your forms in the worst case. So it's one of these great situations where I can tell you a polynomial bound, it's just U2 norm to the 1 over some number, but the number is going to be, if all your coefficients have size 10, then the bound coming out of the proof is C is 2 to the minus 400 or something. It's pretty...
How do these two theorems reconcile?
Oh, sorry. So I think it makes sense. So here, the constant C really does depend on the system of linear forms. So, and what that means in practice is that C depends on the size of the coefficients of the linear forms. And in this case, the coefficients can be arbitrarily large. So then, C will depend on, if P is very big, C can be, like log P or something, or very, very small, or very large.
Coefficients depend on P.
Yeah, so here the coefficients, I didn't make any restrictions at all, so the coefficients are becoming very large. If you like, this is an example of a system of linear forms, they're not fixed on all time, they depend on P, where this number is very, very large in P. It's sort of bigger than log P or something. And so this bound just becomes trivial. Yeah, thank you. Okay, so that was one remark. Second remark was going to be, so this is obviously only a special case when D is 3 and R is 6. I don't know that you can't use the same approach that I'll describe to do the general case, but it's also not true that there's a sort of natural generalization. So there's no obstruction that I know of for general R&D, but also no generalization. I mean, I'll point out a bit later the bits where I just don't know what to do, or without doing a lot more work, which I didn't have time to do before this talk. Okay, so the basic observation behind the proof of theorem 2, I mean, I said that I can prove it just by using the Cauchy-Schwarz inequality, and somehow we thought that the Cauchy-Schwarz complexity was meant to be capturing what you can do using the Cauchy-Schwarz inequality. So I've got to get more out of the Cauchy-Schwarz inequality than we did last time, if I'm going to have a hope here. And the observation can be expressed as saying that the Cauchy-Schwarz complexity is not preserved under Cauchy-Schwarz. So give me an example of what that means. Suppose I take system dagger here, whatever. Let's just call it phi naught, phi 1. So e.g., take phi 1 and look at lambda phi 1 of some functions, f1 up to f6. So this is like, the expectation over x, y, z, f1 of x, f2 of y, blah. Z. And now I'm going to apply some Cauchy-Schwarz to this because that's the only thing I know how to do. So all of these things are bounded by our first Cauchy-Schwarz in this x variable like I did earlier. So I'm going to get x, y, z, y prime, z prime, f1 of x, sorry, 1 is gone now, so I'm going to start at f2 of y, f2 of y prime, conjugate, up to f6 of 7x plus 11y prime plus 17y z prime, conjugate to the half. Okay, and then I'm going to do it again in both copies of these y variables. So I'm going to get expectation over these 2's have gone. What'll it be? X, x prime, y, y prime, z1, z2, z3, z4, some rubbish that I get by doing Cauchy-Schwarz, and then I start off with an f3 of z, and then all the way up to an f6 of some rubbish. But I'm going to think of this as just a system. This is lambda phi prime of some stuff where phi 1 prime has, it has 16, let me see, I have 8 variables here and 16 forms, turns out. And I can ask, it's a reasonable question, what is the Cauchy-Schwarz complexity of this new system?
You're now defining the Cauchy-Schwarz complexity to be the maximum?
Yeah, sorry.
Cauchy-Schwarz complexity at an index?
Yeah, let's ask what this is at this index. Yeah, thank you. So, that's a question. It's a question in linear algebra, right? I'm just saying, given these 16 forms, and I take not that one, can I partition the rest into 2 classes such that, span of this doesn't contain this and span of this doesn't contain this? And I don't know exactly how I'm going to partition them, but there are only 2 to the 15 ways. How hard can it be? Just try them all. And you do that, and it turns out in this specific case that the answer is that it's 1. So if you were trying to prove some theorem that said when you do Cauchy-Schwarz, the Cauchy-Schwarz complexity can't go down, you shouldn't because it's not true, and this is a counterexample. On the other hand, there's no reason to expect it to go down. I mean, we've already seen that I need to apply Cauchy-Schwarz arbitrarily many times. I've only done it twice here, so in general, it's just not going to be true. For random coefficients, it's still going to have Cauchy-Schwarz complexity too, but in this specific case, the Cauchy-Schwarz complexity goes down. I won't try and tell you how you partition these forms. It's an exercise.
In theorem 2, you give some kind of algorithm where if I give you the linear form, you tell me what to do.
Yeah, right. No, you're not on your own. And then specifically, the algorithm doesn't invite you to check all 2 to the 15 ways of. So this proof is not a proof via. This is not a special case of the proof of theorem 2. This is me giving you something ad hoc, which is just an example of why maybe there's some hope here.
But if you use that algorithm to the example you get in theorem 1, what happens?
Theorem 1, yeah, just the algorithm runs for far, far too many steps.
Do you get some bounds that's comparable or not really?
Here, yeah, that's a good question. It comes down to this thing. So at the moment, they're not comparable in terms of working mod P. In the worst case, I might have that I need polynomial in P many Cauchy-Schwarz steps. I don't think it's completely implausible I could reduce that to constant times log P. Unfortunately, it would make the argument much, much worse. It's sort of, yeah, it's already quite difficult to explain what to do, and it would make it even more difficult to explain what to do if I had to get a good bound. So, but yeah, maybe you could get something sharp there. It's not clear. Yeah. Cool. So this maybe shows, yeah, why you might hopefully expect to be able to get some better bound using Cauchy-Schwarz in some cases. And what's really happened here is that we found a coincidence. And the correct way to describe this coincidence is geometrically. So note these linear forms. If I scale them by some amount, just some element of fp, this basically gives me the same thing. Right? I mean, a function of x and a function of 2x are basically the same kind of object. So I can think of these as points in the projective plane. Right? I have vectors of length 3 being the coefficients of my ith linear form, so I'm going to think of that as a point in P2 modulo scalars, so it's a point in P2. And if I draw these linear forms, so as points in, so this is going to be phi 3, it's going to be phi 1, this is going to be phi 2, and then this is going to be phi 4, which was 1, 1, 1. So yeah, this is 1, 0, 0, this is 0, 1, 0, or whatever it is. These are x, y, and z, and this is x plus y plus z. Suppose I now do a geometric construction where I draw a line here and a line here and see where they meet these opposite sides. And then I draw a line through these two sides. Then it turns out, by complete coincidence, that phi 5 lies on that line. Phi 6 is doing its own thing. And that turns out to be what is driving, like, you run this Cauchy-Schwarz argument in 2 steps or 4 steps or how many Cauchy-Schwarzes you need, and it happens to work. And the question, like, why does it work, is because for the particular choices of Cauchy-Schwarzes that you make, it works if and only if phi 5 lies on this line. So if you don't have some sort of numerical coincidence, if you're in this completely general case, give up, it's hopeless. You have to somehow seek out some numerical coincidence. And this happens because, it's a very fancy way of saying that 2 plus 3 is equal to 5. That was in my original choice of forms. This is the coincidence I'm using. But a coordinate-independent way of saying that 2 plus 3 equals 5. OK, so
the 2 and the 3 and the 5 come from form number 5?
Yeah, that's right. Yeah, so.
Yes, OK, so the coefficient of the phi 5, yeah. Okay.
Right, but it used what the coefficients of the other, of 1 through 4 were as well. It didn't use 6, but it did use all of 1 through 5, yeah. OK, so yeah, in terms of believing why theorem 2 should be true, we've established it might work in some cases. We need to find a coincidence. I think it's then not obvious that you can always find a coincidence, and then implementing it using the Cauchy-Schwarz inequality, yeah, that's sort of a different level of thing to expect. I've got sort of 10 minutes. I'll try and explain roughly how the proof of this goes.
So are we to expect that if you have some other coincidence via more steps in the construction, you get a bigger constant?
So yeah, so certainly if you can find a coincidence, whatever that means, and implementing it using only the Cauchy-Schwarz inequality, then the number of steps you have to do to implement it is directly related to this constant. Yeah. However, you might be able to write down a coincidence and then have no idea how to implement it using the Cauchy-Schwarz inequality. I have some ability to sort of program in the Cauchy-Schwarz inequality, but it's not unlimited. So you may well tell me things that I just don't know how to use. So the challenge is to find something that always works and I always know how to do. So I'll describe this now. So, okay, let phi 1 up to phi 6 have true complexity 1. Oh, so I didn't mention, in this geometric picture where I'm thinking of these points in P2, true complexity 1 is if and only if they don't lie on a conic. I mean, sort of believable it's something to do with the squares of the points being linearly independent or something, but that's what it turns out to be. Okay, and then switch to a color that's not black and might work. Okay, so then define phi 5 prime and phi 6 prime by the following picture. So here's 5, here's 6, these are all points in the projective plane. Here's 3, and here's 4. 1 is in the middle somewhere, 2 is in the middle somewhere. Put them a bit closer together. Okay, then to make 5 prime, I take this line until I hit this line, and then follow through 2 until I hit this line, and I get 5 prime. To get 6, I go through 2, and then back through 1 until I get 6 prime. And that's what the points are, like choose any linear forms representing these 2 points, and it's good enough. And the conclusion is that lambda phi of f1 through f6 is bounded by lambda phi prime of f1 through f4, and then some functions, don't know what they are, but they're infinity bounded to the, nope. 16, apologize. So for some bounded functions.
But in lemma 3, so not lying on a conic is a generic condition, but true complexity 1 is a non-generic condition.
In this setting of 6 forms and 3 variables, a generic set of linear forms has true complexity 1, yeah. So, yeah, plenty of examples which don't rely on a conic, but if you just write down coefficients at random, you expect them to have true complexity 1 and Cauchy-Schwarz complexity 2. Yeah, that's a true fact. Yeah, thanks. Okay, so what this says is I can take my system of 6 linear forms in 3 variables and then leave phi 1 through phi 4 the same and mess around with 5 and 6 in this bizarre, strange way. But you know, it preserves a lot of things. I haven't changed 1 through 4, and I haven't changed the line that 5 and 6 are on. Then by sort of applying the Cauchy-Schwarz inequality 4 times and doing a shed load of messing around, I can somehow show that these linear configurations are bounded by these linear configurations. So roughly speaking, I apply the Cauchy-Schwarz inequality 4 times to this. I get some ridiculous number, sort of 56 linear forms in 28 variables or something. And then I sort of progressively annihilate bits of that by sort of merging the functions together or sort of doing less averaging, sort of taking soup norms in various places. And I end up with something which is isomorphic to what I would get if I'd taken phi 1 and then up to phi 4 and then phi 5 prime and phi 6 primed. Okay, my last 5 minutes. So the proof of this, I mean, it's completely disingenuous to say this is by 4 applications of the Cauchy-Schwarz inequality and not tell you how you do that, but it's firstly pretty horrible, and secondly, I can't give good intuition for it in the next 5 minutes. But I can briefly explain why this gives you everything. So it turns out that phi 5 prime is equal to something I'll call sigma 1 arrow 2 of phi 5, and this is 2 arrow 1 of phi 6, where phi 1 to 2 is a Möbius transformation on this line, which I'll call L. Right, so I've taken the points 5 and 6 on this line. I haven't changed the line. I've applied some Möbius transformation, and that takes me from 5 to 6. And the Möbius transformation is do this construction. And then I've taken the inverse Möbius transformation, takes me from 6 to 5 by like doing the construction backwards. Okay, so I can do that. There's a fun fact which says that this construction, well, in this construction, phi prime still has true complexity 1. So by that I mean, whatever this weird thing is, it preserves the property of all 6 points being on a conic. So if their 6 points are on the conic before the thing, then they're after the thing also on a conic and vice versa, which is surprising. Right? I mean, this is a fact in geometry of some kind, that whatever it is I'm doing here can't magically put points off a conic back onto a conic or vice versa. And that's very important because if that weren't true, I would have absolutely no hope of implementing this using the Cauchy-Schwarz inequality. I mean, this statement just couldn't be true. Right? Like I can't take some forms with true complexity 2 and bound them by some forms with true complexity 1. That's just impossible. So this is kind of very important to say that this works. And the next important fact is, okay, I've got sigma 1 to sigma 2 here, but I can exchange the roles of 1 through 4 to get sigma I to j for any I not equal j. 1 up to 4, right? Just permute the coordinates 1 through 4. They all stay the same. And then I get these 12 different constructions that all send 5 and 6 to some different points. Gives me a family of 12 different Möbius transformations. And then if I make some convenient choice, sort of, I don't know, the intersection of these two lines is going to be called infinity, and the intersection of these two lines is going to be called 0, and the intersection of, goodness knows, these two lines is going to be called 1 or something. So if I make a convenient choice of coordinates on L, then some 6 sigma ij's implement. So I can take these Möbius transformations, I can do one after the other in any way I like. I've just got these sort of 6 generators of some subgroup of all the Möbius transformations in the world. If I make a suitable choice of coordinates, then it turns out that if I do 6 of these in a row, I get the following Möbius transformations. And these have the property that if I do these enough times, I can take any point on the line to any other point on the line. I mean, these basically generate SL2Z or index 2 subgroup of SL2Z. And so I can use that to just move anywhere I like. So I can then move 6 to, I guess I could move it to what I've called here infinity. And when I've done that, then I get that 3 points phi 1, phi 2, phi 6 are collinear. And that gives me that the Cauchy-Schwarz complexity is dropped down to 1. So I'm out of time, but in brief summary, right, the reason I can't do this in general is because I don't have an analog of this machine. So if you give me some plausible construction, I can go away and try very hard to do it using the Cauchy-Schwarz inequality lots of times. I don't have a systematic approach that could plausibly work for arbitrary numbers of forms and arbitrary numbers of variables. This is all very specific to the algebra of this setup where I'm working in the projective plane and taking lines and points and everything else. And yeah, if you look at the number of steps you need to do for this, mod p, you can do this in log p many steps or something. And in general, it's like how long does it take you to run Euclid's algorithm on some starting number, which is whatever it is, which could be as high as the size of the coefficients or something. Good, I should stop there.
Maybe we have time for 1 or 2 quick questions.
Sorry.
So this machine of constantly doing Cauchy-Schwarz is somewhat reminiscent of old flag algebra machine. Is there that kind of framework?
I don't know. I guess I don't know how flag algebras work. I mean, right, this whole Cauchy-Schwarz machine I can implement on my computer, right? I have 3 operations I'm allowed to do. One of them is do Cauchy-Schwarz. One of them is take 2 variables and think of them as being the same variable and just forget that they were ever separate. And the last one is kill off some averaging by restricting to some subgroup or some subspace of the original vector space. So I can, any question you can ask, you can phrase in terms of, is there some sequence of these things that gives you the right answer? I don't know of any algebraic way of relating that to the systematic study of flag algebras. Like, that would be very nice. That, maybe secretly I'm doing some sort of, basis. I don't know. Sorry?
It's a more restricted set of
Okay. I mean, that's not a problem. Maybe, I don't know. Okay, yeah, it would be good to know, but I don't know. Yeah.
Related to what you said earlier, but, for a random system of linear equations, do we know how the Cauchy-Schwarz and true complexity are related? Are they always equal? Or?
They're generically not equal. And in fact, the discrepancy gets very big as the dimensions get large. So I think you can just think about some number of forms in 3 variables and ask how these two things, and sort of one is growing quadratically and the other is growing linearly or something. I mean, it's a pretty big gap. Yeah. But it's true in the worst case. Like you can find some system of linear forms where the Cauchy-Schwarz complexity, despite being rubbish, is the right answer.
Excellent. So this is the last talk in this workshop, so I'd like to thank Freddie and all of our speakers again, but also the organising committee of this workshop who've put together a fantastic